Seth Bergmann, and this is a continuation of our discussion of an introduction to the analysis of algorithms. This is part 2. By the way, if there are concepts or terminology that I am using that are not familiar to you, you can learn all those concepts in a free download from rdw.rowan.edu and do a search for Bergmann, and you'll find a book there on Introduction to Computer Science. Free download. It will give you everything you need to know. Let's continue with our analysis of algorithms here. We had looked at 4 methods in part 1, and now we're going to look at another method and find the big O analysis. As you recall, big O of n represents the running time for a method. And when we say big O of n is n, for example, that means the running time is proportional to n, and n represents the size of the input. Let's do another one. This is a method which I'll call M5, and in this method, the parameter is m rather than n. And if I set up a loop in which I begins at 0, and I is continues as long as I is less than n, and increment I once on each iteration of the loop. And in this loop, I simply print I. There I have a method which contains a loop that runs m times. Now the input name is m rather than n. We still say that the runtime for this method is big O of n. So regardless of what the parameter name is or what names we're using in the method, n always represents in some way the size of the input to our computation. Okay, now let's go to the next concept in which we'll have a method named M6, and it will have a parameter n, I suppose, which is an int. Let me get this by just doing a paste. This will be method M6. And here I have the parameter n, and I have a nested loop, and I'm going to put another loop inside my inner loop here. So this inner loop, this loop will be, you lose loop variable k. K is 0, k less than n, k plus plus. And so now I have a loop within a loop within a loop. 3 levels of nested loops. I'll just print out something here. It doesn't really matter what I'm printing out. And so since I have a loop within a loop within a loop, the runtime will be proportional to n to the 3rd power. I'll write that n to the 3rd power. So to be clear, that since I don't have superscripts here in my text edit, I'll write it as n times n times n. Okay, and that simply means that the running time will be proportional to n cubed. If you double the running time, if you double the size of n, the running time will be 8 times as long. If you triple the size of n, the running time will be 27 times as long, n cubed. Okay, let's go to another example now. And this one's a little more complicated. I'll call the method M7. I think I'll do the paste again here. And you can pause your player to look at this in more detail. But here I have a parameter n and a nested loop, but the termination condition on my inner loop is going to be different here. Continue as long as j is less than n minus I, where I is the loop variable for the outer loop. So the first time this inner loop starts up, it will repeat n times. Then the next time it will repeat only n minus 1 times. And then the 3rd time it will repeat n minus 2 times. And so each time the inner loop starts up, it is a little bit quicker. Well, how many times will that print statement execute? Well, when I is 0, we'll have n print statements. And then when I is 1, we'll have n minus 1 print statements. And when I is 2, we'll have n minus 2 print statements. And finally, we'll get to the point where I is n minus 1, and we'll have just 1 print statement. So what is the total? The total number of times that print statement executes? 1 plus 2 plus 3, all the way up to n. And there's a formula for that summation. If you want to see an explanation, download that free download and you'll see the explanation for that formula, n times n plus 1 over 2. A mathematician by the name of Gauss figured that out when he was 5 years old. I don't think I could have done it when I was 35. Anyway, that's our formula for the sum of the numbers from 1 through n. So if the number of times the print statement executes is a measure of the print time, the running time of this method, what is the big O? It's going to be big O of n times n plus 1 over 2. That means the running time is proportional to n times n plus 1 over 2. And if it's proportional to n times n plus 1 over 2, it's also proportional to n times n plus 1. Just use a different constant of proportionality. And let's multiply it out. So that's big O of n squared plus n. Okay, and that big O notation is supposed to represent the running time as n gets large. And we don't say how large, but just as n gets very large, it's supposed to indicate the running time of this method. Well, as n gets large, this term right here, n squared, is going to be much more significant than this term here, n. And so we'll indicate that by saying simply that it is big O of n squared. Oops. Big O of n squared. We just drop out the less significant term, n, and give the running time as big O of n squared in a situation like this. So that analysis comes up very often in computer science, in particular with sorting algorithms. You'll often see a nested loop in which the number of times it repeats is 1 fewer each time, and it's still big O of n squared. Let's do another example now. This will be, let's see, name this would have been M7, just to give a different name to all my methods. This would be M8 now. And in this method, we'll have a loop that repeats n times, just like in the other methods. But now what we're going to do is call M5 with the parameter n as the actual parameter. So this appears to be a simple loop, and we would be tempted to say it's big O of n because it contains a simple loop. There's no nesting of loops. But let's go back and look at M5. Here's M5. M5 itself is big O of n. It contains a loop. So each time we call M5, that requires big O of n, and we're calling it n times, so this is big O of n squared. What we essentially have here is a nested loop, because M5 is big O of M, N. Okay, and the message here is watch out for hidden loops. I call this called M5. I say there's a hidden loop in that method because we don't see it unless we go back and look at the source code for M5. Let's do one more method here. Method M9. And here my parameter is going to be a list. Some kind of list. Let's make it a list of integers. Not that it really matters what kind of list it is. And in my loop, I'm going to set up a loop variable. I is initially 0. I less than list.size I plus plus. And inside the loop, I'll simply print out each element of the list, list.get position I, and print it out. So that loop will simply access each element of the list and print it out. Well, first of all, the main difference here is our parameter is not an int. Our parameter is a list. And we need to recall what n is supposed to represent in this big O analysis. N is supposed to represent the size of the input. And so in this case, for method M9, n represents the size of the list, the parameter. Okay, so that means if n represents the size of this list, the loop is repeating n times. Now let's look at this get method. Is there a hidden loop in get? Well, having coded that method, we know that there must be a hidden loop there if the list is a linked list. With a linked list, we start at the first position and work our way down to the ith position, and there's a loop involved there. With the array list is backed by an array, and we have direct access to each element in the array. There is no looping there. So whether or not we have a hidden loop depends on what kind of list that is. If it's an array list, no hidden loop. If it's a linked list, there is a hidden loop. And so the big O runtime will depend on what kind of loop that is, what kind of list it is. And so we'll say for an array list, the big O runtime of this method is big O of n, because there is no hidden loop, we just have a simple loop here. But if it's a linked list, it's n squared, or n times n, because each time get is called, it starts up that hidden loop again. Watch out for hidden loops. Here the running time depends on what kind of list we're given. Here it's just declared as a list, and we don't know whether it's an array list or a linked list. Well, I think I'll call it quits there. Look for part 3 coming up soon. Thanks for your attention. And don't forget that free download from rdw.rowan.edu for everything you need to know to understand what I'm talking about here.